So I think the following part will be presented by Leonid, who was the person mainly behind settings of this problem. So we together discussed how it could be translated into a computational form, and he put a lot of efforts. And I think it is very good talk for him to describe what he did and what could be the next steps for further development of this problem. So how could your solutions work in real life scenarios? Okay, so Leonid, please go ahead.
Okay, thanks, Andrei. Sergey.
Yep.
1 second. Could you see the presentation?
Yep.
Okay. So, hi everyone. My name is Leonid Grimachich. I will talk about data analysis for satellite tracking, which is the first part of IDAO competition. So the objective was to build a model that would predict future position of satellite objects given previous observations. It's the main objective. 1 second, sorry. Yeah, satellite tracking is one of the most important tasks in astronomy because of there are a lot of the number of satellite collisions and conjunctions is increasing. Also, it's very important to calculate maneuvers efficiently to save propellant and extend satellite life in orbit. Also, in our case, it's very important to save time for telescopes on finding a space objects. It's very difficult and challenging to obtain a model, physical model that could solve our problem, because on the one hand, it's we don't know the form of satellite objects and other parameters, and it could be not just satellite, or it could be space debris or unknown object, which parameters are unknown. On the other hand, mathematical and physical models can't take into account a lot of factors. For example, Earth's surface, like mountains and so on, or solar pressure. There are several partners are engaged in this project. Our Laboratory of Methods for Big Data Analysis, also the task is provided by Astronomical Science Center. This center is engaged in the system for observation space objects. Also, they take part in maintaining the catalog of Earth satellite orbits, and also they target telescopes. And the third partner is IDAO Data Analysis Olympiad. Thanks for them. There are several state-of-the-art approaches. For example, these 2 papers, which try to use only machine learning for to solve this task without any models, any physical models. Maybe it's a good idea to try something with machine learning and with physical model, but there are some approaches like that. So about IDAO competition, the participants had to develop and explore machine learning models to improve prediction of submodel, which is a GP4 model. And the answer should be true position, which is positions that was generated by another model, general mission analysis tool, which is created by NASA. There were two tracks. In IDAO, first one is about just maximum score, and the second one, in the second track, participants had to send scripts, which were run on contest machines, and there were some limited computing resources. Participants had 2 months of data. So the first month we were with true data, true positions, and simulated positions. And the second one contains only simulated positions. So the participants had to obtain true positions by simulated ones. The positions of satellites were to 1/24th orbit, and there were 600 satellites. On the right, we could see some absolute error of 1 coordinate for random satellite. So it looks like that. Quality metric was CMAP, some kind of CMAP, because it provided an opportunity to normalize our data, so we could compare different objects with different height and different coordinates in one metric. But this metric had some drawback because it can't take into account the vector nature of the data. For example, 2 vectors on the slide are close, but considered like non-close in this metric. Maybe in future we will change this metric to another one, and we discuss it later. So during the IDAO, it was CMAP metric, but with some modifications according to contest system. In the future, we will maybe use this kind of CMAP. So it's analog, but with vectors. So in this case, previous drawback doesn't exist. So participants, on average, the best participants improved the SGP model forecast by 50%, and there are a few approaches on the slides. Mainly, the most of participants use linear and polynomial regressions models, translation to into different coordinate system, for example, into orbital elements. Also, the most of best participants use clustering points by positions in orbit and predicting position by other points from the same cluster. Usually there were 24 clusters for each 1/24th point of the orbit. Also, participants used random processes, sinusoids, and some machine learning stuff like gradient boosting, staking, ensembles, soft regression, and so on. There are some finalists we should definitely congratulate them. And next steps in this project are on the slide. We will use participants models to determine a position of space objects comparable to optical accuracy of the telescopes. Also, it will be important to determine not only position of the center of mass, like in IDAO, but also make the center fall into the viewing angle of the telescope. Also, there are a lot of difficulties with real data. For example, time steps are uneven, and there are some positions error and the telescopes error, and so on. Also, we will take into account the strong influence of solar pressure. Solar pressure is very influencing of the influence of solar pressure will be taken into account, and in IDAO competition, this coefficient were, and also it was varied according to some function, each defined period of time. So several times it was varied during the data generation. We could see that in case of low solar pressure, the IDAO model, which is green line, is much better than just SGP for prediction. On the slide, we could see absolute error. And in case when solar pressure is high, we could see that it's hard to predict something, and some IDAO participants' predictions are not so efficient. So we will research these cases and solar pressure. Now the laboratory of methods for big data analysis of our university and Astronomical Science Center are engaged in this project, and if someone have questions or interested in participating, you could write about yourself to this mail. Thanks for attention. Please, questions.
Thanks, Leonid, for the slides. Okay, everyone, if you have any questions to Leonid or Andre about the task or the area, that's the right time to address them. And please don't hesitate. Yeah, if you wonder how you can address the question, there is a chat box, and you can write your question in this box. And yeah, we will see it obviously, and Leonid or Andre will answer. Okay, Leonid, Andre, we have a first question. Do you see it in the chat or?
Yeah, I see.
Okay.
1 second. Yeah, we didn't include additional information because actually we don't know that. We don't know exactly solar pressure coefficient or form of space object or some information. We could know only their positions from the past, or and do some simulations. And in some cases, that's all we have. How should we need to clean data? So I don't understand the question actually.
Yeah, the question about how we need to clean data. Could you please specify what do you mean by this question, so we will be able to answer properly. And we have another one. The reason why some satellites have 23, 25, not 24 points per circle is solar pressure.
Well, I don't know what is circle of is solar pressure. It's not exactly 24 points. It's some, if I'm not mistaken, some random period of time. Thank you, Mohammed. Well, the question about Kaggle is for Sergey, I think.
Well, it's a tricky question. The reply would be also tricky, I guess, that we didn't want to be another data science competition in a way and organize something on the Kaggle automatically or just another one. Secondly, we bear in mind when IDAO was just created, we wanted to combine somehow approaches of Kaggle and ICPC. And that's why we decided to do something separate, you know, to have a platform where we could potentially combine these two approaches. I guess that was the initial reason for this. Yep, I hope that we covered the question.
Well, Sergey, I didn't see some successful solutions with neural network, if I'm not mistaken. Some of finalists used them, but so the neural networks were in scripts, but they didn't use them. Maybe I'm mistaken, but I didn't see. Hiroshi, well, I think there were some mistakes in data, unfortunately. So a lot of the most of participants cleaned data and just keep some points. It's quite difficult to me to read the name. Sorry. About HGP4 to make a data set to add additional information to other than coordinates and velocities. Yeah, it was available and participants could do that. Also, it could be possible to add all information they needed. But no one did that. But yes, it could be possible. Max, this is a good question. A good question about jumps. Maybe I could answer later. You could mail us. Well, a logic, if I'm not mistaken. The simulated data is not so good, for example, because it doesn't take into account solar pressure at all. It's one of reasons. Maybe, for example, the influence of sun and moon Are some maybe because of that it's hard to predict, but the main cause I think is about solar pressure. Kairaf, maybe I don't know. Sergey, could participants or other people get the data set?
Let's discuss it afterwards, because I mean, the data is yours, and first of all, I think only after the final is done. So I think afterwards we can think of releasing the data in the task. Yeah, I hope that answers question.
What will be the best way on your perspective to tackle this problem? It's hard to tell. Maybe I think we will do something like combine the best participant models and try it on real data. And maybe after that, we will have some things about it. Well, about guns, one of our students try to do that, try to use a generative adversarial network, but now there are no any results yet. But it could be useful. Well, thank you for questions.
So if there are no additional questions, I think we can move to another part where some teams who qualify to the final will share the solutions. In meanwhile, afterwards, we will still have a section for questions, so we can come back to questions afterwards. Meanwhile, I will add to the communication another speaker. Give me a sec. From the team Data Plomo. Okay, Max, can you join us?
Yeah, I think I'm muted.
No, we can hear you now.
Okay, good.
Perfectly. So yeah, I'm giving the stage to you. You can share the screen if you have slides. If you don't, you just can enchant us with your talks. Okay.
Let me see. I've never used Zoom, so I just have to check out how to. Yeah.
Yeah, you have like a tool line, and there is a like green button that states share your screen.
I just have to quit Zoom and come back to share my screen for permissions.
Okay.
Just a second.
Yeah, surely. Okay, meanwhile, maybe while Max is unplugged, maybe we can have another question, because I can see one. I know. Okay, Max is back, and I tried to add him again. Max, you here?
I think I'm in. Yeah.
Yeah.
Okay, so I'm just sharing my screen. Okay, can you see my screen?
Yeah.
Okay, great. Okay, so hello everyone. Thank you for being here. So my team was called Data Promo. We're three in our team. The three of us are PhD students. I'm in my third year of my PhD. I'm finishing. And Raphaël and Robin are in their first year. And we're based in Toulouse in France. So yeah, the context, I mean, Leonid just gave a lot of information, so we won't go on to that. Specifically, we're going to talk a bit more about track 2, where track 2, we had to build a solution that can make predictions in less than 60 seconds, and which consumed less than 500 megabytes of RAM. Yeah, originally we thought that we had to train our model under 60 seconds, so we actually went a bit crazy and tried to optimize everything, and then we realized that that wasn't the case. So yeah, So yeah, we quickly noticed that the data was really periodic. So how to say, if you look at a lot of the sinusoids, a lot of the coordinates, they're really periodic. So we straight away realized that it was quite obvious that we had to build a model which took into account past observations to predict the future. However, there are some systems, so Leonid just said maybe because of the solar pressure, some satellites where the coordinates deviate. So yeah, we just hoped that we could build a model that was able to detect these changes and still be able to learn. But yeah, so in a nutshell, this is our solution. So to remind everyone, this is the solution that got first on track 2, but I think it scored second on track 1 too. So we used the same solution for both, like we didn't change anything in the code for both tracks. So we had one model per satellite and per coordinate. And in each case, we built an autoregressive model where we took the 48 past observations, so 2 times 24, and very simply, we trained a linear regression to map the next coordinate, next position, based on the last 48 values. And that's it. That's really it. We wanted to keep it as simple as this because of the 60 seconds and the megabytes of RAM. So yeah, I think in the end, it took our solution 55 seconds to run. So yeah, that's just under the limit in Python. So the trick really is when you build an autoregressive model, you predict the next step, and then you take that prediction and use it as a feature for the step ahead. So once we predict for step n+1, we use that prediction as a feature for predicting step n+2. So we essentially just roll forward, okay? So I'll get to that later, but that does incur some technical difficulties, but nothing impossible. And yeah, we validate on the 40% last of the data, 40% last of the data. Yeah. So initially we built a really simple model. This is before building the autoregressive model. We noticed that the data was completely periodic. So we took each position of every cycle. So we realized that the cycles are mostly periodic of period 24. And so we took each position. So for example, maybe you see the mouse on my screen, period 10, which is like the light blue. And so for every 10th moment on the period, we took that value and just fitted a line to that. And we noticed that most of the time this is a straight line, so this worked quite nice. And so for the steps ahead, we just can simply just propagate the line forward and get the predictions. But then we tried to generalize this, and instead of just using the values of the previous positions at every position in the cycle, we want to use all the data. So for example, for the third point, we would use the 2 sine waves that predecess it, not just the values on the positions. So yeah, it makes sense because the data is periodic. So it's like time series. We may as well make use of that. And yeah, and basically in code for training, for every satellite and every coordinate, we build a vector of features, and each vector contains the 48 past values. So in this instance, you can call it P. And therefore we obtain n feature vectors, where n is the number of satellites times the number of coordinates. And we have n future targets. And then for forecasting in the future, well, we predict the next step, and then we append that prediction to the feature vector, and then we just remove the oldest value. So we always have p values. Okay. How do I get this up? Okay. So it's a flexible framework because we're able to plug any regression model into this framework. We use the linear regression, but you could just as have well used a decision tree or what else. It's a bit like a generalization of ARIMA models, but for any kind of regression model. And there are a few papers that discuss this. I can link them afterwards. And also, in our case, we only use the 48 pass values, but nothing stops you from using extra features as long as you can estimate them online, because of this rolling forward thing where you have to add the features to the feature vector every time you make a prediction. So yeah, so the model we built was kind of sequential. You have to predict and then to append the value and then predict in order to predict for the next step. So it means that you have to call predict a lot of times. So for every satellite, for every coordinate, and for every day in the future, you have to call predict. And in our case, we use scikit-learn. And this incurs a lot of overhead because scikit-learn is meant to make a prediction for a batch of data and not for a single element. And so we kind of stripped the scikit-learn classes we used so that they do not do all this data validation and check-in every time we call predict. And this is the key point that allowed us to go under 60 seconds. So in code, it's really, really simple. So for example, we use a standard scaler to scale our data and a linear regression. Instead of using the default implementations from scikit-learn, we overrided the transform and the predict functions to only compute the bare minimum. So in the case of a linear regression, instead of checking that the data was the right size, etc., and it was numeric data and an NumPy array, we just called np dot. We just called np dot and we added intercept. And this is actually 30 times faster than calling scikit-learn by default. Same goes for standard scaler. So you can't click on the links probably, but I can send the slides afterwards. Since then, we've also learned about sklearn ONNX, which is an implementation of that allows to convert a scikit-learn model to an ONNX model, which can make predictions online much faster. It's the same kind of ideas. Now, in terms of memory usage, instead of submitting to the platform and waiting to see if it crashes or not, or if it fails, we found this Python package called Memory Profiler, where you run a script and it gives you a nice chart where you can see your memory usage as the script is going. So this is on my laptop and it took 36 seconds, and you can see that there's a peak of around 400 megabytes. It's actually doing a pivot table. This script was really useful for us to debug when in the script things were going haywire and how to fix it. Yeah, and so we tried a few things. To be fair, we could have tried a lot more things, but we were quite comfortable being first, so we didn't have the hunger to keep trying sometimes. But we did try Gaussian processes, and it worked really well. It fitted the data really well because you can fit sinusoidal kernels, which makes a lot of sense for this kind of data, but it wasn't able to generalize in the test set. And the same goes for NBeats. NBeats is this neural network model, which is meant for time series. And again, it was able to understand the sinusoidal nature of the data, but it wasn't able to generalize to the test set. And also, we tried to improve our model by not predicting for each coordinate, for predicting the 6 coordinates at the same time. But this didn't really bring any improvements. It did make things faster in terms of speed, but not in terms of accuracy. So yeah, our model is just a linear regression, and we use scikit-learn, but we believe that, and this is because of our work, our jobs, our everyday jobs, we believe that it's a good idea to try to look at this from a point of view of online learning, where you can train the linear regression with stochastic gradient descent. And so every time you get a new ground truth, the real satellite values, you can update the weights of the linear regression and keep training. So instead of training on 1 month of data, you would update the model every time a new value arrives. And so, and our solution, which just uses past values and is a linear regression, is completely can completely be transferred to an online model. And so we, for example, we've written these libraries in Python called Cream and Chantier to do online learning and make it a bit easy. And yeah, so just if we had some advice to give, it'd be that just keep things simple. In particular, this data is not crazy data. There's not a lot of noise and there's a lot of structure that you want to keep, that you want to use. So you have to try to think about what your model is learning and what you're doing. So we try to not go heading and do a random forest or XGBoost. We just thought, let's build something simple and with simple ideas. Yeah, it's always good to validate locally and to every time you make an improvement to commit your work and, so you stay sane and you're able to reproduce what you're doing. And yeah, we always spent a lot of time to doubt everything we did and to double check and make sure that the data was clean, because we did realize that there were some gaps in the data and that cleaning the data was really important. Yeah, that's it from us. So the code is on GitHub. Again, I'll put the slides and the GitHub link on the chat. That's it. Thanks for listening.
Thanks a lot, Max, for a nice presentation of your solution. And yeah, if you share afterwards with me the presentation, I will be delighted to send to all participants. And
yeah, I can. Yeah. I'll put it in the chat now.
Yeah, thanks. Okay, Ron, if you have questions to Max and their solutions, please feel free to address them. Max, I'm not sure whether you can see the chart right now. I mean, you probably do, so we might have questions over there. So first of all,
I can see a question from Leonid, I think.
Yep.
Yeah.
So do you mean to train online one model for all space objects? So
we don't train online, but indeed, if we did have to do it, I mean, both would be possible, I think. I think one of the key problems to the thing with the solution was that we had to build one model per satellite because every satellite had a sort of different domain. If you were able to normalize the data so that each satellite had values in the same domain, the same frame of reference, then you could build a single model. But indeed, if at the moment, and if we were to put it into production, we would build one model per satellite. Yeah. I don't know if that makes sense. There's also Norbert who's asking if there's a specific reason if we chose 48. Actually, well, we picked a value of 24, obviously, because the data was periodic of period 24. And actually, we tried 48 for every satellite and every quadrant, and it worked. And we were first with that solution. So actually, we never really, I mean, I think I tried locally to 72. It didn't improve, but definitely if we were actually trying hard, we would grid search and try different numbers per satellite and per quadrant. But again, we wanted to keep it simple.
Thanks again. So any other questions to Max?
Yeah, definitely. I mean, some models explode and we're aware of that. So there's two kinds of explosions. There's the explosions where it happens in the training data in January. So we're able to see that. And I think our model takes that into account. But when the data explodes in the future, in February, we don't know that. And that's true for every participant in the competition. So we didn't worry about that in a way. Again, as I was saying, if you build a model online, you're not training on 1 month and predicting another month. You're able to learn every day, maybe potentially. So you're able to capture that drift. I think it's just, in this case, it doesn't make sense to build a model for 1 month to predict the next month. You really want to update and learn every day so that you're able to capture the deviations and the explosions as quick as possible. But for sure, yeah, our model probably, like many other models and other participants, exploded. But again, it was impossible to know, if at the end of February it would explode because no one knows. So it was kind of the same situation for everyone. Yeah. Yeah. Well, as I was saying, I'm not sure, but I think that some satellites. So Andre is asking about periods 23, 25, 24. We think that what other participants think that the satellites have period 23, 25. It's just that there's a gap in the data. There's like these steps. And if you look at the data, sometimes you'll see that between consecutive observations, there's a time gap of like 0 seconds or like a few milliseconds. Whereas most of the time it's something regular, like a week or an hour or a minute. And so the first thing we did was to clean our data and remove these gaps. And so, yeah, then it kind of looked like it was periodic of 24. I hope that makes sense.
So I guess let's do the last question for this block and then we'll move to another teams if you don't mind.
Sure, yeah.
Sure. So we have the last one.
So Abhijit's asking if we tried Armor and Cymax. I tried Armor, I think, but I didn't try it very hard and it didn't really work. As for Cymax, well, the data is not very seasonal, so there was no, I mean, it is seasonal, but we're already picking that up. As for the X in Cymax is, I think it's exogenous variable, so that means extra features. Again, we did not add extra features, but our framework was capable of taking that into account, but we didn't try it. As I said, we actually got a bit lazy and because we were first, but there's definitely a lot of room for improvement. Or not. I mean, maybe that just keeping the model simple is the key. No.
Yeah, thanks one more time for your participation. I think still afterwards we will have another block with questions. If you have questions, you can write them, and afterwards maybe Max also will be able to answer them. Or we have a chat on Telegram, so we encourage any dialogues over there. So
okay.
Yeah. Meanwhile, I will add the second team.
Okay. Thanks.
Thank you.
Ouais, c'est bon. Cool. Mais j'ai peur, je crois que enfin, il y a deux chats, c'est ça? Non, c'est bon, j'ai arrêté.
So now I'm adding another team, also Boost. So give me a second. So hi guys, you should now be able to speak and enable your share screen features. Yeah, does it work? Hi there.
Hi everyone, can you guys hear me?
Yeah, we now, and we can even see the screen. Thanks for joining us, and I'm giving up the stage to you.
Oh, okay. Hi everyone, we are Team LZ Boost from Malaysia. Okay.
I'm not sure whether you speak now and show because we are not able to hear or see anything.
Hello?
Yeah, now we can hear.
Okay. Okay. We have Alvin from Mimos, and we have Jinsen and me. Okay, next. Oh, so in terms of the IDAO, what we did initially we checked the actually the data, and we noticed that there is the XYZ and VX, VY, VZ are periodic signal, and most of the satellite have 24 epochs, and because of these properties, points from different cycle at the same part of the cycle can be approximated by the simple function. If you can see the figure on the right side, what I mean by the points from different cycle is indicated by the red line. So we can actually fit a line to predict the projection of the points. Okay, next. So what we did is we use curve fitting using SkyPy optimized package, and a line is fitted into every data points for the 24 FBARs, and for each of the VX, for the XYZ, VX, VY, VZ. And we noticed that some of the satellite have 25 or 26 FBAR, but we actually try using different 24 or 25 or 26. Then we found out that using 24 is giving a better overall result. So in the end, we use 24. And the line that we try to fit is linear, quadratic, and cubic, and sine. And which equation to be fitted is based on the SMAP and also the ratio between RMSE between different equations to prevent overfitting. And next. So this is our pseudocode. So if we see there is a change in the sign of the curve, then we try to see the snap of the sign. And if the ratio between the RMSE of the cubic and the linear is 0.3, then we fit a cubic, else we fit a linear. Then if the snap of the sign is less than 0.5, then we fit a sine. Then if there is no change in the sign of the curve, then we fit then we do the same thing to compare to the cubic and the linear. Then if anything that fills above, then we fit a quadratic. And the parameter that we use, the 0.5 and 0.3 in the pseudocode above, are actually determined when we try to compare the result. Okay, next. Yeah, and this is our fitting result. On the top left, the figure A, this one is fitted by a cubic, and the orange line is the X stimulated, and the X is the true position, and the green line is actually the projection of the true value. So for figure A and B and C, it seems the curve is fitting well. But for figure C, I'm not sure whether the line will go downwards later or will go upwards later. But it's something that we can check if we have more data in the future. And for the figure D on top left, we actually fit a sine curve. Then it's actually quite good in terms of the prediction. Okay, I think next slide. Yeah, and thank you and stay safe.
Thanks one more time for presenting your solutions. So if you have any questions to the team, please do not hesitate to ask right now. Yeah, okay, there is a question. I'm not sure, can you see the question in the model part in the slide?
Yeah, I can see the question. Is there a model part? Okay, for the first question, is there a model part in slide? We actually fit the curve. So we did try the linear, quadratic, then cubic and sine. So we actually didn't train any model. It's pure curve fitting. Then for the next question, how do you decide model is good or not, or any metric? Because after we first try our solution, then we actually sit on number 4, I think. Then after that, we didn't improve anything. So yeah, then we just stick at our solution. Can you share the GitHub? Yes, after this. Yeah, any more question? Predict, yes. You predict the point coordinate using the past 24 points. No, I'm not using the past 24 points. So if Elwin can show the previous slide. Yeah. For the question with for the past 24 points, we actually, if you see on the figure on the right, so we actually fit a line on the every point on the red dashed line. We didn't use the past 24 points, but it's every 24 points.
Yeah, there are two other questions. Did you use cubic linear scene model for the whole test period or for some range? The first one.
We actually didn't assign any test data. So we fitted the, when we try to fit the curve, we actually use the whole month data. We didn't use any test data. Yeah, Jin Fei answered it already. So our leaderboard is our validation. Could you please repeat how you validate during fitting? Oh, okay, I think Jin Fei already repeated it. Oh, for maybe Alvin can show the pseudocode. So, okay. So if there is a change of the sign of the curve, that means it's a U curve or U curve or N curve, then we try to fit a sine curve. So if the SNAP of the sine curve is greater than 0.5, which means most probably the sine curve is not fitting well. So we try the cubic and linear. And for cubic and linear, because when we fit the cubic, we actually want to avoid the overfitting of the cubic. So if the ratio between the cubic and linear is 0.3, then we use cubic, but if it's more than that, then we use linear.
So let's do the last question and then move to another team, if you don't mind. So yeah. Any last questions? So it seems not, but anyway, as I said to the previous team, that if you have questions to this team too, you can write to the IDAO chat on Telegram, and we quite encourage any communication. So in there, and don't hesitate to use it for the right purposes. And thank you guys for presenting and answering questions on your part. Thanks a lot. So up next is another team. They actually didn't reach high positions in either of tracks, but probably they had the most beautiful nickname in the whole competition, which was actually Atom Emoji. So I'm not sure how to announce them correctly. So Atom Emoji team, I will just give me a second. I will. Hi, Ivan, Igor. Yeah, you may start. Or do you experience any technical difficulties?
Hello, can you hear me?
Hi there. Yeah,
oh,
yeah,
nice.
Yeah, surely.
I'm sorry.
No worries. I just have one quick question. I cannot find in the list of participants the third member of your team, which is Vladimir. He's not participating.
Maybe he missed the time. I don't know.
No worries, because you asked to add all three, so that's why I'm asking. Okay, so you two are here, and we are most grateful for your participation and for your fantastic name. So now I'm giving the stage to you, so please.
Okay, hello, my name is Ivan. Our team is from the Joint Institute of Nuclear Research. We are not very good with machine learning, so we didn't use any. So, of course, we tried everything when we started. So we were trying machine learning and processing data and cleaning and everything. And every model that, when we tried using one model per satellite, it was very slow. And also half of our team didn't like it because it wasn't very general. So, and the solutions that use the output for the next cycle of prediction grew out of control very fast, so it was exponentially growing instead of predicting very good. So, so machine learning initially failed, and then we tried to get a better baseline instead. So what if we predict not the X, Y, and Z, but the differences? So how they are different from the simulation. And if we see that the differences grow and they are periodic and
rather big, so it's not very easy to predict the differences. But what if instead we move to the space of Kepler parameters? So the parameters that describe the orbit. So two parameters describe the size of the orbit, the eccentricity of the orbit. Three parameters describe the position of the orbit in space, so three angles compared to the equator, and so on. And one parameter you can choose whatever one you use. There are several approaches. Describes the position of the satellite on this particular orbit. So as it goes around in circle, the angle grows in cycle. So the most direct one is this theta. This is actual anomaly. So it's the actual geometric angle that the satellites makes with the center of the Earth. And
Ivan, can I have a quick question?
Yeah.
Do you show slides? Because if you do, we cannot see them. Sorry.
Oh, sorry. Yeah, I'm trying to show slides, but I think you can see them. Okay.
Yeah, there is a button.
There's a button. I didn't push the button.
Yeah, sorry, because I realized that you were referring to slides. Yeah, sorry.
Okay,
I do apologize.
Let me try. I think I should. I'm not using Zoom for anything else, so it's new for me. Sorry. Okay,
well, I mean, we're all in this position nowadays to increase our
share
usage of different apps.
Screen number. Which one do I want to share?
Yeah, you can actually pick what do you want to share, like particular app or program.
Let's try screen 2. Do you see my second slide? Oh,
nope.
No, let's share.
Yeah, now I think, yeah. Yep.
Yeah, nice. Okay, so let's start from the start. Hello.
Yeah,
and
sorry again for inconvenience.
Yeah, and we failed at machine learning in all these different fantastic ways. And yeah, here. So the difference between the simulated and the actual data grows, and it grows kind of unpredictably, and it is periodic, so it's not very nice. But if we use this Kepler parameters that describes the orbit and the position on the orbit, we can see that the orbit doesn't change very much, it just drifts a little. And the periodic position is kind of easy to predict because it just grows periodically. So here it's eccentric anomaly, so it's just an old term that was in Kepler times, but it's still used. It's just the angular position of the satellite on the orbit. So it grows to pi and then jumps to -2 pi and jumps to -pi, so obviously. And m is just this kind of parameter, but it grows linearly. And this is why it is easier to predict from time to jump to m. But I will return to that. So technically, to go to Kepler parameters, there are several libraries. Of course, we could just do them ourselves, but it is hard. So we use libraries, but most libraries are object-oriented, and most of them work on one orbit quickly, but don't work very well when we have 600 orbits. So we just took two functions that we needed from PyCap library and rewrote the actual code of the function using NumPy variables instead of floating point variables, and it was just fast and it worked. So now we have, we can translate the X parameters into Kepler variables. And as we see, actually, the simulated data that we are given is basically we start from the Kepler variables at the start of the time frames, or at the start of the month, and it's just constant. What if we predict the difference when starting from the end of the month? So we take the Kepler parameters from the end of the training data and just predict that the orbit will stay the same. And then it would be easier to learn this small difference than to learn this large difference. Unfortunately, we didn't have time, so we just predicted the actual Kepler parameters without any deviation, even small one. But anyway, so we can predict that the 5 parameters that describe the orbit will stay the same because they drift very slowly, but we have to predict the anomaly that is the position on the orbit. Well, we can very easily predict the mean anomaly because it just grows linearly with time and then jumps back to minus pi. But to go to the physically interesting one that actually lets us predict X, Y, and Z, which is at least eccentric anomaly. There's this formula that goes easily one way, so we can construct the mean anomaly from the eccentric easily. But to go from M to E is not possible directly, but we can just use SciPy to solve it approximately, especially because it's a simple function. We know the first derivative and the second derivative. We give them to the SciPy optimized Newton, and it quickly finds the E that corresponds to the given M. And so more as an exercise than it as a actually necessary part, but maybe if we had more time, it would be even more useful. We wrapped everything, including preprocessing, into scikit-learn transformers and created a pipeline that just removes byte points with DT0, which is not necessary in our situation, but we just had it for any other experimentation. Transform XY to Kepler parameters, predicts the 5 constant parameters, predicts the M to be periodic, transforms its M into E using that Newton solving procedure, and just transform Kepler parameters into XY. And this is a training pipeline, and this is a prediction pipeline that just gets the 5 constant parameters from the last time that are saved into CSV and just are loaded as when creating the model. And the M, so the time at the last point of the month is also saved, so we know exactly, so we don't lose a phase. We don't lose any time. And so these are loaded into this part of the pipeline, and then we do the same thing. We transform mean anomaly into eccentric anomaly. We transform Kepler into except the parameters that we need, and we get the orbit. And this is our prediction pipeline. So, and here you can see the results. And this is our, not the oldest result. Unfortunately, I don't have the graph for the submission. This is a previous approach where we didn't have the actual anomaly prediction. We just took 24 last points and said that anomaly keeps repeating, so it is worse, but you can see that it is much better than simulated. So our approach worked. And the last optimization that we had that I think probably gave us the last position out of 20 teams instead of just losing outright is that we used not the baseline from the last point, but the baseline of the last orbit. So we took the 24 last points in the training data, and we averaged the Kepler parameters, and we took that as our constant that will keep going. Thank you very much. I'm ready for questions.
Thank you, Ivan. So everyone maybe have questions on the solution?
So we had a little bit of time to try to learn something that will improve from this green line to the actual red line, but nothing we tried worked, and we didn't have a lot of time, so we just gave up at the very, very end.
Please don't be too shy to ask. So yeah, we have the first question. Yeah, can you see it?
I don't know. I don't think so.
So what was the coordinate translation error significant?
Coordinate translation error from... I don't quite get the question. I'm sorry, I don't understand the question, sorry.
Leonid, you can actually join by voice and then maybe explain additional question if you want to.
Yeah, okay. Thanks for the presentation. It's very interesting. I wanted to ask, I used some translation functions from standard libraries and from some Python libraries, and I obtained the quite significant error during the translation.
You mean from initial parameters to Kepler?
Yeah, from initial parameters to Kepler and vice versa. And that I obtained some error during the
I think maybe your function used not eccentric anomaly, but real anomaly. Maybe there it's approximated. I'm not sure.
No, maybe it was about 1% or smaller.
The thing is,
but I didn't use PyCap actually.
Maybe it was a bad library, and I think maybe the only place where it's approximated in any way is in the anomaly phase. So all the other parameters are easily calculated, just calculated, and it's all. If the Kepler parameters in your library return you the mean anomaly, then maybe they approximate the anomaly translation worse, but I'm not sure. I'm not an expert.
Yeah, okay, thank you.
Any additional questions? Yeah, I mean, since this is the last team and the last part of the webinar, maybe you have like overall questions to maybe to the previous teams, maybe to the task creators. Oh, okay, we have another question. So can you see the question in the chat box?
Okay, let me see. I don't know about this GP4. It was just the only solution that gave us the best results, but I'm not sure about this GP4. We just use the Kepler parameters from the end of the month, and the simulation data that is provided is using Kepler parameters from the beginning of the month, as I understand it. I don't know.
I also could say that we expect that a lot of participants will use Kepler orbits, Kepler parameters, but they didn't.
So I guess no other questions from you guys, or maybe there are some last ones.
Hello, my name is Igor. I'm from this team. May I ask a question?
Sure.
So this question is more to the task. And Ivan, could you please open your slides again and just go back to the slide with the graph which you show? So because the question is that, so at first we tried to use some neural network to predict actually you see the graph, it is a differences between the real data and the simulated data, and our idea was that they are very periodic. But on this picture on the left you may see that at the beginning the prediction, the simulated coordinates are quite good, and then something happens which makes them just worse, and then something else happens and they just become even worse. So is there any answer why this happens, and could this particular moment be predicted? Because for me it's not still so clear. Thanks.
So I think it was a data bug, and maybe just these mistakes were cleaned by every participants, almost every participants, like Max discussed.
Okay. Okay, thanks. So it just required data cleaning first to get rid of this, and then there was much better to predict.
Yeah, another explanation could be so we change the solar pressure coefficient during the data generation, and maybe this point is just about that, just the points where we change the coefficient.
Okay, thanks. That's clear now.
Yeah, okay. I think it's maybe time to wrap up the session for today. And I would like to thank all the teams, the creators of the task, for joining and presenting all materials today. And for the task, for the teams, I would like to ask whether you could send me the materials so I would be able to share with all other participants what you have presented. And yeah, as we actually indicated in the message to all you guys, that we are planning to do this like couple of other sessions of this kind on different areas with our various partners. And yeah, I hope that we will keep you occupied until we meet again during the final, so which probably will take place around the fall. And we definitely will try to give you the final dates and information as soon as possible. But I hope you understand the situation with COVID-19 now. And yeah, I guess we're all in the same boat now from wherever country you are. So, but anyway, let's finish on something positive. So thanks a lot for participating today, and keep in touch. If you have any questions, you have me on Telegram and you have a chat, and you have our official email. So don't hesitate to address. So thanks a lot, everyone. Hope to see you all soon.